So today we're going to talk about another application of the first and the second derivative. In fact, we're just going to focus on the first derivative in this video. And in the next video, we're going to make use of the second derivative once again. So let's say you have a function. We have our xy plane here. Let's say you have a function that is sort of like a parabola, or it is a parabola in fact. Let's call that f of x. And let's choose a point P, so that's going to be an arbitrary point. Let's have the coordinates x0 and y0. So y0 and x0. So let's have, if we know that if we find the first derivative of the function at this point, that's going to give us the gradient. So the gradient is going to be a tangent line to that. Now, for the sake of argument, let's say we call that tangent line t. And let's say we were interested in finding the equation of that line at that point. So we would obviously have to use the equation for a linear function to find what that equation for t would be. And let's say also that we were interested in finding a normal line at that point. So that would be a line that is perpendicular to that tangent line. And we will call that normal line n. So what is the equation of a straight line? Well, for t, it would be simply this. It would be y minus y0, which is the point we have chosen for y. And it would be the gradient m of the line at that point times x minus x0. But what is the gradient at that point? Well, the gradient at that point is just going to be the first derivative of the function itself, evaluated at the point x0. So this is going to be a numerical value that we're going to input in here. And similarly, if we wanted to find the tangent line at any other point, we would use the same, but we would change the coordinates that we're using. So now, what about the normal line? Well, the normal line is going to be defined as follows. Because it is perpendicular to the tangent line, we know that the relation between the gradient of the normal line and the tangent line should be the following. Perpendicular lines have this relation between the gradients, so it should be the negative reciprocal of that gradient. And what is the gradient of t? Well, the gradient of t we just discussed is just this, so this is going to become minus 1 over f prime evaluated at x0. And all of this implies that the equation of our normal line is going to be the following, equals to minus 1 over f prime x0 times x minus x0. So let's see if we can apply this to an example just to show you how it works. So let's have the following function. Just gonna get rid of this. Let's have the following function. We have yx equals to 3x squared plus 2x. And let's say we're interested in the point 1, 5. So let's find the first derivative. That's going to be 6x plus 2. And now let's say we want to find the equation for the tangent line. That's going to be y minus the point y, which is 5, equals to the gradient. So what's the gradient going to be? Well, the gradient at this point, so that's the x coordinate, is going to be 6 times 1 plus 2. That's going to be 8. 8 times x minus 1. So this is going to become 1 minus 5 equals to 8x minus 8. And we can rearrange this as y minus 8x plus 3 equals to 0, or y equals to 8x minus 3. So this is what we will end up getting. That's the equation of our tangent line. Now let's say we're interested in the equation for the normal line. Well, it's going to be the same, but the gradient is going to be the reciprocal. So it's y minus 5 equals to minus 1 over 8, x minus 1. And if we multiply both sides by 8, this is going to give us, and let's make that negative as well, minus 8y plus 8 times 5, that's 40, equals to x minus 1. And we can rewrite this as 8y plus x minus 41 equals to 0, or y equals to minus x over 8 plus 41 over 8. So this is essentially what you would use, and it's a really interesting application of the derivative because it allows us to find equations of lines that are either perpendicular or tangent to a particular point along a function. And that's quite useful because in some cases we may be interested in drawing some shapes or trying to investigate the geometry of something that is happening around that particular point. But this is just one of the many applications of the first derivative. And in the next video, we're going to discuss how the first and the second derivative can be combined to solve problems in optimization, which is all about finding maximum and minimum values of specific functions.